Hello, am I audible?
Yes, ma'am.
Yeah, okay. So I know it's 6, but let's wait for a few minutes in case more people are joining.
Okay, ma'am, sure.
Okay, I still only see two people. Okay, three people now. Maybe we'll just wait for one more minute in case people are still joining. Um, yeah, I'll just share my screen in the meantime. Okay. Okay, maybe we can slowly start and people can join as the time passes. Okay, so it's already 6:05, so I'm just going to start the meeting. Okay, so hello everyone. Welcome again to these problem solving sessions that I am holding as part of your NPTEL course on particle physics and the standard model. My name is Zenia. I am a astrophysics PhD student and PMRF at IISc. And as I've mentioned previously, the field of astrophysics that I work in, which is high energy astrophysics, has a lot of connections to a lot of the things that we'll be discussing. And of course, particle physics is very fundamental to any branch of theoretical physics, not just astrophysics. But yeah, so it's really great for me also because by teaching these sessions, I'm given this opportunity to kind of refresh my knowledge as well. So anyway, so my name is Zenia. I am in charge of taking these problem solving sessions. The idea is that these are live sessions, interactive sessions, as opposed to your recorded videos. So you're going to have an opportunity to every week have 2 hours where we can kind of recap the course and then we can discuss if any of you have doubts. And we'll also be solving some problems together. The problems are going to be related to, but not exactly your assignment problems, so that once you know you solve them, you have some familiarity, it becomes easier for you to do your assignment questions as well. And again, please feel free to mail me throughout the week for any clarifications. Something I really appreciate is if you can also mail me regarding, any agenda that you want me to discuss. Right now, I just look through the syllabus and I pick out topics that, I try to recap what was done and I try to pick out some topics that can be further expanded on. But if you have something particularly that you want me to discuss, then I can also center my slides or my week's discussion about that. So because this is, this is kind of a, sorry, yeah, because this is a, what can I say? Because this is an interactive session, the ball is really in your court. You can really, ask that please cover this or that, in more detail. Maybe you saw it in the lectures and would like to see it again. Okay. So all these sessions, as you know, probably know by now, for past 3 weeks, whatever sessions I've taken have been recorded. The videos are available on YouTube. So I'm going to just show you that if you just okay, sorry, if you just go to here, yeah, here you can see that this is my website. Here I maintain a page with all the links of all these recordings. So for example, if you go to this YouTube playlist, you can actually find what is given here in terms of particle physics in the standard model, the NPTEL stuff. So you can see that the recorded lectures are there for the last 3 weeks. Also, if you go here, you can find the slides of the sessions here. Okay, so this is the idea. Okay, so right, so this is the idea behind this. I've just copy paste the link in the chat. You guys can save this link, and from there you can access all the recordings as well as the slides of the sessions. Okay, so this is the idea. So without further ado, maybe we can go to this week's lecture. So this today we are going to be discussing week 4 material and solving problems related to your week 4 assignment. I think currently you had have started your week 5. So this is kind of like a recap for you. So we are for now moving past discrete symmetries and on to continuous symmetries of the standard model. It's very important to understand symmetries and how to represent them mathematically, which is using groups. And that's why I kept saying that group theory is kind of like the grammar of the standard model or the language of the standard model. We need to have this mathematical framework in which we want to write the standard model, all its particles and all the different interactions between the particles, and for that we require group theory. And since we are dealing with both quantum mechanical and high energy scales, we need to combine quantum mechanics and relativity together, and that's why we need quantum field theory, which is QFT. You saw the first application of what is relativistic quantum mechanics, or the first approach towards relativistic quantum mechanics in the terms of the Klein-Gordon equation, right? So these are all the things that were covered in this week's lecture. So you're starting to slowly see the kind of mathematics that you will be encountering and one of the central themes that you will be encountering in this course. Is there a question? Oh, am I not sharing the screen? Uh,
Ma'am, you are visible to me.
can everyone see my content? I thought I am sharing. Okay, I'll just stop sharing and reshare. Okay. Mm, okay. I don't know what happened. I'm just going to share again. Okay. I hope you can see. Can someone confirm?
Yes,
Yes,
ma'am,
I
I
can
can.
see. Yes.
Okay, so then maybe the person who's having the issue, I hope it's sorted out. If not, you can try leaving and joining again. Okay, so as I said, to describe standard model particles and their interactions, we require a mixture of both quantum mechanics and special relativity in the form of relativistic quantum mechanics, or in other words, quantum field theory. Okay, and the first approach towards quantum field theory, or the first kind of idea towards making a relativistic quantum mechanics theory, is a Klein-Gordon equation, which you derived and saw this week as well. So all these are kind of laying the framework for when we will move on to Dirac equations and other things, which will be more towards describing the interactions of the standard model. Okay, fine. So, so today I wanted to kind of again encapsulate these early ideas of quantum field theory from a very quick, amateurish perspective. I am not a particle physicist, but whatever knowledge I have of quantum field theory, I wanted to kind of convey to you. And I think this quote by Sidney Coleman, who is one of a very distinguished particle physicist, is kind of relevant for us, as you will see, which is that the career of a young theoretical physicist consists of treating the harmonic oscillator in ever increasing levels of abstraction. Okay, and you'll see exactly what this means, because in some sense the whole of quantum field theory is about this quote exactly. Okay, so, all my quantum field theory, I'm just going to give you a very quick overview of whatever small amount of QFT you require for this course. Again, whatever you require for the course will be taught to you in the course itself, but just to give some added context, I've made some slides. My reference for this is actually there's a book, it's called Quantum Field Theory for the Gifted Amateur. It's not a QFT textbook. I would not recommend it if any of you are, wanting to take a QFT textbook. You should go with one of the classic books like Peskin and Schroeder or Sedrinki or whatever is recommended in the course. But this is basically an overview. It's a slightly it's a little more than an overview. It's it's a kind of a conversational textbook where you can learn a little bit of quantum field theory without going too deep into some things, right? Because quantum field theory, as you might have seen from your textbooks, can be a little bit heavy on complex ideas and mathematics, and this is a book that's actually very lightly written in one sense, which is good because we can grasp the ideas quicker. But again, I would say that if you want to learn QFT properly, like in a course or something, don't use this as your only textbook. You can use this as supplemental material. In any case, because our focus in this course is kind of the standard model and we want to use QFT as a tool to understand or build up the standard model Lagrangian, I thought we can use some ideas from this textbook, and then I wanted to present it to you. Okay, so yeah, this is the book title is Quantum Field Theory for the Gifted Amateur. So you can already see that it's not written for completely a layperson audience. It's written keeping, physicists in mind. So you need a little bit of, again, quantum mechanics and working knowledge of special relativity, but it doesn't go too much technical into the details. So again, if you want to use it as a QFT textbook, that's your prerogative, but it's not fully comprehensive like some of the standard texts are. It is a, I would say it's good for what it is, which is like a reference book that can give you exposure to a bunch of ideas at a glance. It's a very good book. It covers a lot of topics, and it's written in a fairly simplified way. But again, the problem with simplifying things is sometimes the simplified details are actually important. So with that sort of disclaimer, I'm just going to borrow a few things from their pedagogy so that I can communicate some QFT ideas to you. The book is by Lancaster and Blundell. You can just search the name and it'll probably come up online. Okay, so as I said, the basic idea behind quantum field theory is that we want to describe everything in the universe, every particle and every wave in the universe, as an excitation of a quantum field defined over all of space and time. So instead of, with classical mechanics and with quantum mechanics, we very much deal with, particles, point particles, especially in Newtonian mechanics, we deal with point particles. And even if we have extended bodies, we come up with, terminologies like the center of mass, so that we can still apply our kind of point particle idealized formalism, right? Even when it comes to the motion of planets, Kepler's laws and all that, we do assume point particles in some sense, right? So we deal with localized positions in space, but of course quantum mechanics tells us that that's not true. We don't really have particles localized in space. They do have some wave behavior, so they are spread out as little probability packets, right? But still we are dealing with maybe one wave function as a time. Instead of that, we are going to now promote our particle or wave packet based thinking. We're going to promote that to a field theory. And I'm sure all of you are already familiar with at least classical field theories, because you've all taken electromagnetism courses, right? You all know that we think of electric and magnetic fields, right? When we have a charge, you often do calculations about charges in forces in electromagnetism, without really worrying about the charges or the magnetic, not monopoles, but let's say the magnetic dipoles that have sourced them. We kind of assume that the charge exists somewhere, and that has led to whatever electric field configuration or magnetic field configuration we want. In fact, we don't care about the charge anymore. We actually just care about what is the electric field which permeates the space, right? We can draw field lines to represent it and so on. So this is the basic idea behind uh, a field theory, right? You put in some coordinates and out comes some function of the coordinates, which is what we call this field. And this kind of function is defined over all of space and time. And that's why we have a field. Now, a quantum field is where, instead of dealing with classical field theory, where we deal with classical particles, here we actually deal with quantum particles. And we'll be writing Lagrangian and Lagrangian densities, which correspond to that fact. So here again, as I said, the thing about quantum field theory is that kind of gives us a framework to unite quantum mechanics and relativity, which is very important for us in the context of particle physics. And now, right, so you can just to go through this again, every particle and every wave in the universe is simply an excitation of a quantum field defined over all of space and time. So we're going to, instead of dealing with the electron or the proton or whatever it is as the fundamental quantity, we're going to deal with the quantum field which produced it itself, right? The electromagnetic field has an excitation which we call the photon. And similarly, all the particles we know are sourced from fields. And this is the kind of thinking that we are going to be shifting towards. So again, we put in coordinates, we get the value of a field. Instead of thinking of a localized space or time, we think of all over the plane itself. Okay, so quantum field theory relies on something called second quantization. So it's a little more complex than what I've written here. But again, because I'm using the pedagogy that QFT for the gifted amateur use, I think it's a pretty nice way to put it, which is that the first quantization is to realize that particles can behave like waves. This is what, for example, De Broglie and other Planck and the other people who kind of, spearheaded the discretization of quantum mechanics realized, is that just like light has a sort of particle and wave nature, the same way, if light waves can have a particle nature, the same way particle waves can have a particle matter particles can also have a wave nature. And this was probed by things like electron diffraction and other things, and that's what led to De Broglie's famous formula. So second quantization is to realize that waves can in fact behave like particles. And this may seem counterintuitive because we just, discussed about light. But when we say waves behave like particles here, we mean a slightly different thing. And here, this particle nature of waves is actually what's going to allow us to write down quantum field theories. Okay. And this is where the whole harmonic oscillator is going to come in, that I hinted towards with the first quote, which is that, the career of a young theoretical physicist consists of treating the harmonic oscillator in ever increasing levels of abstraction. So let's see where the harmonic oscillator comes into all this. So let's start with the most simple wave phenomena associated with the harmonic oscillator, which is of course a mass on a spring. This is a very classic system. You can solve it classically. We know that quantum mechanically, if I write the Schrodinger equation for this, it looks like this, right? This is the momentum squared, this is the potential, and this is E psi, this is the wave function. And you know that if you solve it, you can get some complicated functions and some energy levels, right? And this is an exercise that we all do in our simple harmonic oscillator is a very simple exercise we all do in our first quantum mechanics courses, which is that we can solve for the wave function of the harmonic wave functions of the eigenfunctions of the simple harmonic oscillators and their corresponding ladder of energy states. Of course, we can do this by simply plugging it into this differential equation and solving it using, standard differential equation techniques and, knowing about some special polynomials called Hermite polynomials, setting the boundary conditions. Just from a regular Schrodinger equation perspective, you can solve for this question. But what Dirac realized is that there's another way in which we can actually do this problem. So, what Dirac realized, and this is a very interesting insight, is that when you look at the Hamiltonian of this system, which is p square by 2m, again, I'm just writing the operator back into its operator label. So, just momentum squared by 2m plus half m omega x squared. This looks like some sort of a square plus b square kind of thing. So, Dirac said, oh, can we factorize this? So, okay, some kind of factorization is attempted for this object, but of course, this is not a perfect factorization of this because remember, these are not numbers, right? They are operators, and the difference between scalars, scalar numbers, and operators is that operators don't commute. And in fact, we know that momentum no, don't necessarily commute. We know that momentum and position definitely don't commute because that is the heart of the uncertainty principle. So when we write this kind of factorization, that's actually not perfectly true because the cross term is not going to cancel out because of the, as I said, because of the non-commutativity of the momentum and position operators. So altogether, what I get is if I actually write this factorization, if I actually do the multiplication and other things and I write it down, I get an extra term which comes from the commutator, which is basically from this x times p minus p times x, which doesn't cancel out as it usually does in a number situation. So basically, this looks like the Hamiltonian that we just wrote plus one extra term. And this extra term is just comes out to be minus h cut omega by 2. Why is it minus h cut omega by 2? Because x comma p commutator is I h cut, right? So it's just from, again, this is all elementary quantum mechanics. I'm sure you have all seen this approach to the um, uh, to solve the harmonic oscillator. And you know that this kind of approach is what leads us to define something called the creation and annihilation operators. And we can rewrite our system in terms of these new creation annihilation operators. These are not Hermitian operators, so we cannot observe them directly, but their product, which is A dagger A, is actually called the number operator, and it just defines the number level of our energy state, and that actually occupation number of our energy state, and that can be defined. And of course, we can write the position and momentum in terms of these creation and annihilation operators, and that's exactly why the Hamiltonian can now be rewritten in this form. What is the benefit of this? When we apply the annihilation operator on a state, it just gives us the lower state with the energy level it just produces the lower eigenstate. That is when we, sorry, I said that wrong. The creation operator, if we apply on a state, it just gives us the next higher eigenstate. So, for example, in this ladder of states, if I apply the creation operator onto the state ket1, say, then it gives me some value times ket2. And similarly, the annihilation operator brings me one step down the ladder. So, this is how you can think of why they have these names as well, is because if you apply this combination of the position and momenta on states, they end up giving you some way to scale up and down the ladder. Again, I'm not going into the details because I think this is what it's known. For example, you can see that all the different states here are represented by different kits, and the creation operator brings us on top, whereas the annihilation operator gets us down. And if you apply the annihilation operator on the uh, uh, zeroth state, it just gives you zero, right? So, yeah. So the creation and annihilation operators create and annihilate, which we know, a quanta of energy, h cut omega, in the energy ladder of states. So creation operator gives us an extra h cut omega, whereas annihilation operator gives us a lower h cut omega. So essentially, from the wave equation, which was describing the simple harmonic motion, we've got something like a particle behavior, right? Where we are getting these energy packets like h cut omega packets from this creation and annihilation operators. So it looks like a wave problem is now producing particles, which is exactly what I said about second quantization, right? So first quantization was again De Broglie's insight about matter waves, particles which we know to be particles behaving dually as waves, whereas second quantization is where we have wave solutions like this, but from some different way of looking at their Hamiltonian reveals that they may have some hidden particle-like natures as well. So why is this important? Because now we can actually generalize this to n harmonic oscillators, and this is usually what are called the modes of a system, right? So even when you wrote the Klein-Gordon equation this week, you would have written the different eigen modes of that system. Each mode is nothing but a harmonic oscillator. And you can see that the different creation and annihilation operators among the different harmonic oscillators, so to speak, have some particular commutation relations and so on. And these are things that you saw. Maybe the normalization might be a little different in the lectures that you saw, but the idea is the same, right? We basically have now a way to describe a system, even a wave system, in terms of these modes of excitation, which we represent, which represents their inherent, sort of particle-like behavior in terms of these different harmonic oscillator systems, in terms of their creation and annihilation operators. So this is the heart of quantum field theory. This is called sometimes the second quantization or canonical quantization. This is a very sort of very simplified look at canonical quantization. In reality, it's a little, you have to be a little more careful when you do these things, but I'm just trying to give you the funda behind it so that you can have an idea when you look at the textbooks and other things. So there is, you have to do proper mathematics for this, and you should look at the proper text as well. I'm just trying to give you some funda so that you can appreciate the case as well. Okay. So one more important ingredient is, as we are dealing with quantum field theories, the quantum statistics becomes important. And we discussed quantum statistics in much detail last week when we spoke about the spin statistics theorem. Essentially, we know that at the particle level, when we get to again high energies, relativistic energies, it becomes important not just to consider, Maxwell-Boltzmann like behavior, but actually particles can have two distinct classes of behavior based on what kind of particle they are. There are two kinds of particles in the universe. They're either bosons or fermions. We know that bosons like to clump together, whereas fermions don't. Well, because fermions obey the Pauli exclusion principle. In other words, bosons have wave functions that are symmetric under exchange of particles, whereas fermions have wave functions that are antisymmetric under exchange of particles. This becomes very important when we are dealing with indistinguishable particles, because we are dealing with particle physics. We are going to be, as was hinted to you a few lectures ago, and some of you had asked, we are going to be dealing not with Hilbert spaces anymore. We are going to be dealing with Fock spaces, right? And in Fock spaces, you can have particles being created, being decayed, being annihilated. The particle number is not conserved. And when you have groups of particles and they are interacting with each other, it's important to know what kind of statistics they follow, right? What is the basic tenet of the particles that they follow, which is basically whether they're fermions or bosons. So that also has to go into this sort of, when we construct the harmonic oscillator, right? When we construct this harmonic oscillator formalism to describe our particles and their interactions, we also have to keep in mind whether they are bosons and fermions. And this is exactly how, by the way, you can prove the spin statistics theorem as well. So remember that last week, for instance, or even in the lectures, you saw kind of a cursory topology based proof for the spin statistics theorem, where we were looking at how, spinners obey rotation rules that are slightly different than the ordinary vectors we are used to, and that shows that, for example, they can lead to antisymmetric wave functions like what we see in wave functions that pick up a -1 on exchange. But to actually get the mathematical proof, you can actually use these kinds of ideas of quantum field theory to prove the spin statistics theorem. So again, I'm not going into the math details of any of these things. I'm just trying to give you some sort of flavor for these things or funda for these things so that you may um, go ahead and look at it more seriously. So you can see that now we are going to draw an analogy from our simple harmonic oscillator where we have different quanta in the oscillators. The kth oscillator would just correspond to, that just corresponds to different particles in momentum space. So, the kth oscillator just corresponds to the mth momentum mode. And again, you did this again when you solve the Klein-Gordon equation in your lectures, which is that you expanded the Klein-Gordon solution in terms of eigenmodes. These eigenmodes you can think of as being different kinds of harmonic oscillators. So that's why again the Sidney Coleman quote is relevant. So now the energy is simply, you can see how it takes identical forms in both the formalisms. Okay, so now since we are dealing with field theories, we have to now talk about how do we write down the equations of motion of the field theories, right? So obviously, as I said in the beginning, Newton's laws and classical mechanics are largely, the Newtonian formalism of classical mechanics is largely based on this sort of what can I say? um, Particle based notion, right? Whereas we can, then there are alternate formalisms like based on Lagrangian or Hamiltonian mechanics that can be um, further generalized to actually fields. And we'll be using these kinds of Lagrangian Hamiltonian concepts when we want to deal with field theories, because they are more easily generalizable when compared to just the point particle based dynamics that we see in Newtonian mechanics. Okay. So here you can see that this is basically, instead of defining in terms of Hamiltonian and Lagrangian in terms of just, like kinetic minus potential energy or kinetic plus potential energy at a point as we usually do. Instead of going from the particle picture, we are going to be talking about fields. So we have to integrate over the entire space that the field is in. So instead of talking about Hamiltonian and Lagrangian, we'll be having a Hamiltonian density and a Lagrangian density, which is integrated over d cube x, as you can see, right? And you can see that both the Hamiltonian density and the Lagrangian density are functions of the various coordinates that are there. You can also write a conjugate momentum. So all this is based on the usual kind of Lagrangian mechanics that you have. So once you have this idea of, okay, I shouldn't just write the Lagrangian for a particle. Now I'm dealing with a field. So how do I write the Lagrangian for a field? I have to write it as an integration over a whole point, right? It's similar to how we talk about probabilities and probability densities, right? Like the Maxwell-Boltzmann distribution is a probability density function, right? We integrate the Maxwell-Boltzmann equation over space to get the over the velocity space or whatever it is to get the probability that a particle has a velocity between, say, v1 and v2, we have to integrate over that space. The same kind of way, here we are talking about Lagrangian densities or Hamiltonian densities. And once that switch is made in your head, you can just write conjugate momenta as you usually do in your Lagrangian mechanics. You can see that the Hamiltonian and Lagrangian densities have the same relationship that Hamiltonian and Lagrangian do in normal Lagrangian mechanics. And now the action can be written because the action is L times dx, where L is the actual Lagrangian. Now we have to replace Lagrangian by, script L, which is the Lagrangian density d cube x. So altogether the S becomes d4xl, right? And this is also relevant for when we want to find out the sort of dimensions of a field theory. We have to use this idea because the action is always dimensionless, and from setting this equation up, we can actually find out what is the dimensions of the field theory that we are setting up. And this you might have also done in this week's lectures. So this is again from your action principle by looking for the principle of stationary action, which again we discussed, I think, in the very first of these problem solving lectures. I discussed the principle of stationary action very briefly to do with the Noether's theorem. But in general, yeah, just this just comes from the fact that nature chooses the paths that stationarizes the action, either maximizes or minimizes it. And if we just do the mathematics, this corresponds to something called the Euler-Lagrange equation. But instead of writing in terms of the Lagrangian, we now write it in terms of the Lagrangian density. So now we have promoted our equations of motion to field equations simply by replacing the Lagrangians and Hamiltonians by Lagrangian densities and Hamiltonian densities. Okay, so are there any questions at this time? I'm just going through a lot of things, I realize, but I'm just going through them a little fast because, first of all, you've seen some of these concepts already in your lectures and in past classes. Secondly, yeah, the point is not, this is not a quantum field theory course. If this was, we would do it very differently. The point is to give you an idea or a jumping point to discuss these things. And then later you can, in your own time, you can pick up an actual quantum field theory textbook like Peskin Schroeder or something, and then you can work this out or understand with some added context in mind. Okay. Okay, great. Just give me one moment. I'm just going to be back. I'll just get some water and come back. Just give me a one. Yeah, hello. Sorry about that. I just had to get some water. Okay. So, right. So now we are slowly building up. What I'm trying to motivate for you is that we're trying to slowly build up the different ingredients of a field theory. So first of all, we saw about a little bit about second quantization, which is that the waves that we describe can have some quantization or quanta or particle information contained within them, and this allows us to expand them in terms of eigenmodes and all that stuff, right? And this is linked to the idea of canonical quantization, which is what leads to QFT in the first place. The other thing is, now when we write the equation of motion of a field theory, we can't just stay with, our sort of particle based equations of motion. We have to promote our Lagrangians to Lagrangian densities. And once you do that, you find that the rest of the equations follow and have the same form as before. So you can see that, you know, solving the Euler-Lagrange equation will produce all the allowable modes of oscillation and hence the allowed wave vectors, the particular values which occur without dissipation. By the principle of superposition, we can kind of take a weighted average of all of them. And many classical continuous systems may be expressed in Lagrangian formalism so that the Euler-Lagrange equation allows us to derive the normal modes. Our experience with the simple harmonic oscillator motivates the idea that these normal modes are simply simple harmonic oscillators themselves and then can be quantized, leading to particle-like solutions. Okay, so there are two things, right? One is that, okay, we can write the Euler-Lagrange equation in terms of, field theory. We can write in terms of these Lagrange intensities and other things. So then I get, these different modes of the system. Each mode corresponds to a harmonic oscillator. I can then quantize that harmonic oscillator. Remember, waves behave like particles. That quantization leads to, whatever particle excitation comes out of the field itself. So for example, if you do this whole procedure for the electromagnetic field, then the quanta that arise from this are the photons. Similarly, from quantizing other fields, you get other particles. From quantizing the QCD field is how you get gluons and other things, right? So this is basically a classical field theory. The thing that makes it quantum is the fact that we can quantize the different modes leading to particle-like solutions, and those quanta is what makes us there. Okay, so again, I'm not going through the mathematical machinery of how electromagnetic field leads to quanta of photons. I think it is better, equipped to take a full quantum field theory class for that. A quantum field theory is a semester long course. I'm not going to attempt to teach it in 30, 40 minutes like now. But I'm trying to give you an idea or motivation of what is happening or why we need these things. Okay. So, finally, let's quickly look at relativistic quantum mechanics, which you started looking at this week. And first of all, let's look at the Schrodinger equation, right? So the Schrodinger equation is actually non-relativistic. How do we know it's non-relativistic? Because in essence, the Schrodinger equation is nothing but E is equal to P square by 2m. This is the non-relativistic energy equation. The way to get the Schrodinger equation is simply we can promote all of these to operators. So you'll see that E can become operator E, which you can write in terms of the time derivative. P becomes, of course, the momentum operator, which is in terms of a space derivative. And then you get this kind of equation for the Schrodinger equation, right? So this comes, and of course, if you have a potential, then that comes some plus V term comes, right? But the point is that this is based on a non-relativistic energy momentum relation. We know that in relativistic mechanics, energy is not related to momentum in this way. We have to write it in terms of, E is equal to square root over P square C square plus M square C power 4 kind of form, right? Which is the actual E is equal to mc squared equation. But, everyone is content to do the zero momentum case in, that's another discussion. But anyway, so this kind of already tells us that the Schrodinger equation is non-relativistic. So if I want to get a relativistic theory of quantum mechanics, let's try to do the same procedure for a relativistic energy, right? So as I said, in relativistic mechanics, energy has this form where we have to also consider the rest energy of the particle itself, because E is equal to mc squared, and take the, oh sorry, This should be m squared c power 4. I'm so sorry, that's a typo. I'll see if I can just insert a, yeah, just, okay. Okay. Right. So, okay, so we know that in relativistic quantum mechanics, sorry, not relativistic quantum mechanics, in relativistic mechanics, energy and momentum are related using this E is equal to p squared c squared plus m squared c power 4 whole to the power of half. Let's do the same procedure we did before, which is let's promote to operators where E is now replaced with the operator form and P is replaced with, the operator form in terms of the space derivative. And if we now plug it in, you can see that we get some other equation, interesting looking equation, but this actually has a problem. And this problem was discussed in the lectures. So what's wrong with this equation? What's wrong with this way of writing? There's a square root. Yeah, exactly. And why is the square root problematic? Why is there a problem if there's a square root? Yeah, expanding it gives higher order terms, sure. Or in other words, what is the issue if there are higher order terms? Let's say there are higher order terms. So what? Equation is harder to solve, maybe, but what's the issue? Physics issue, not maths issue. Exactly. We have treated now space and time differently then. Exactly. So you can see that on one side you have something that looks like a derivative. Here we have again something like a derivative, but as someone correctly pointed out, this is actually a square root and expanding would give some higher order terms, which means that on this side we have something that's like a first derivative of time. But on this side we don't have something that's a first derivative of space. We have some other higher order terms as well, right? And this is a problem because the whole point of special relativity was that space and time should be dealt with on the same footing, right? Or in other words, this whole theory becomes non-local, right? Because right, I'll just put that square. This whole theory becomes non-local because now we have treated space and time derivatives on different fruits, on different foots, uh, different fronts, I guess. And because of that, we don't have locality, we've not no longer preserved the tenets of special relativity, which is that the speed of light cannot be violated, right? So that's why this becomes a non-local theory. So clearly something with a square root is we have to throw out. We can't do this. So, okay, instead, let's try by writing the equation like this. Let's write E squared is equal to P squared C squared plus M squared C power 4. Instead of starting with the square root equation, let's just square on both sides. Let's get rid of all square roots. Then this issue is gone, right? And then again, if we do the same thing, which is where we are substituting the energy with its and the momentum with their respective operators, you can see that we get something like this, right? Minus h cut square d square phi by dt squared, and then you have something the basically the what is this called, the gradient square has a name, I forgot. Together they are the D'Alembert, but this alone is having some name. I forgot the name. And then m squared c power 4 acting on phi, where phi is now some field, which is a phi is some function of the space and time coordinates. And this is basically what is the Klein-Gordon equation. Yeah, Laplacian. Thanks. I had a total brain fog moment. Yeah, so this is the Laplacian and this is the d by dt squared. If you combine them, you can actually write them in relativistic way, because again, we can write it as a 4 vector as del squared just by combining both of them together, plus m squared is phi is equal to 0. So when you write it in this form, you kind of also do an extra step, which is that you assume natural units. Natural units are where h and c are taken to be 1. A lot of high energy physics and particle physics is done in natural units. You might find these weird expressions where it looks like, things dimensionally don't match up. Remember, there are always hidden powers of h squared and c squared that are missing. Okay. So, yeah, if you ever find that something dimensionally doesn't add up, just imagine that, first check whether they have used natural units or not. So this is basically the Klein-Gordon equation, and now it looks like, okay, everything is fixed.
I
Schrodinger
have a
equation
question about
out.
the previous slide. Can I
Yes,
ask?
yes, yes.
Okay, yeah. Here we have h bar squared, del squared, phi, del t squared, and square root here. Oh no, where's the square root? There
There's
should
no
be
square.
square.
There's no square root here.
Oh, the previous one then, the one with square root. Yes.
Yes.
So here to remove the square root, you multiply from left with the Hamiltonian, right? Then we should have a del square, del t square here, and the square root should be removed from here. In that
Sorry.
case,
Yeah, can you repeat? It was not clear. Can you repeat?
yes, okay, to get rid of the square root, to
Yes.
multiply from the left with the Hamiltonian.
Uh,
Hamiltonian, which is
okay.
then, I mean, let this term h bar square c square delta square plus m square c to the power 4 be written as h. Then if you multiply from left by h, it will be del by del t h psi, and which will again be equal to del by del t psi.
Okay, so we are not
And
okay, we are not squaring this equation because this equation is problematic, so we don't want to deal with that. Instead of that, we are just square before promoting to operators itself, we are going to square the energy equation itself. And then we'll substitute the operators so that everything is clear. Otherwise, as you say, psi can be stuck here and there. So instead of that, we are just going to square the energy equation itself. From there only we get the Hamiltonian anyway. So in that case, you will get exactly what I've written here.
okay,
Yeah.
thank you.
Okay. Yeah. Yeah. Because this is again, we can square this, but again, this is an operator and then there's wave function involved. So to keep it clean, we start over from the beginning. First, we start with equal to p square by 2m. That gave us Schrodinger. When we use this equation, we got some wrong non-local equation. And then instead, we tried change this to the squared version. We got the Klein-Gordon equation. And that is basically the D'Alembert or the 4 vector version of the Laplacian plus m squared phi is equal to 0. Again, here I have set h and c to 0, sorry, h and c to 1. Uh, those are the natural units. A lot of particle physics is done in natural units, so always have a look out for that. So, okay, so Schrodinger equation non-relativistic, Klein-Gordon, great. This seems to solve everything. But actually, there's a twist because Schrodinger actually derived the Klein-Gordon equation first. Before, when he was trying to find out the sort of quantum mechanical equation of motion, he did also try to do this thing, but he found it to be problematic and actually he had discarded it. So, what is the problem with the Klein-Gordon equation? Well, the problem is with probability densities. So remember that quantum mechanics is a probabilistic theory, right? Where that is the whole idea behind the famous Schrodinger cat thought experiment, which is that the wave function basically gives you a way to, if you integrate over the wave function with its conjugate, you find the probability to find that particle in that space. So the probability goes as something like the wave function star, the complex conjugate of the wave, the basically the norm of the wave function, right? And if this is a time dependent quantity, as this equation seems to suggest, then we can actually write a continuity equation for it. So you can have the probability density and you can have an association probability density current, or probability current density as it's sometimes called. And this you would have also done in your normal quantum mechanics, which is that you can write this current density of probability, basically how the probability is changing over time, sourced in a current. You can write it in this form. Not going into the details, you can find the details in any quantum mechanics textbook. And that gives us a way to estimate the probability density from that probability current, right? And if we write this in a covariant form, because again, remember, we are dealing with four vectors, we are going to be dealing with relativity, so we can't just stick to normal vectors. Then we have to write it in this form of four vector form. All the sort of normal nablas get replaced by delta mu. Okay. So what is the issue now is that if I just take this and if I substitute any to the power IPX, which is actually the solution to the Klein-Gordon equation, as you can show, I forgot to put a slide on that. But if you solve this, sorry. If you solve this equation, this is basically a wave equation. So similar to how free particle gives you wave packets in Schrodinger equation, you can also solve and find something similar in the Klein-Gordon equation. But if you put in that solution, you find that the time component of the current density comes out, which is basically the probability density, comes out to be 2n squared times E. Now, E can be either positive or negative, it's just the energy, which means, as you can show by solving for this equation, you can show that E actually takes positive and negative values, which shows that rho actually, which is related to E, seems to be either positive or negative. So this is what bothered Schrodinger, which is that when you solve the Klein-Gordon equation, you get a class of solutions for phi. But then when I try to interpret phi in terms of a probability density, again, don't worry if you didn't follow all this mathematics, you can sit down and try to work it yourself. It's not that difficult. I'm just going through it a little quickly because that's not the focus of this. The point is that if I solve the Klein-Gordon equation, I get this kind of solution which admits both E positive and negative. And that seems to imply that if I try to give this the quantum mechanical, probability density kind of interpretation, I seem to get something like a negative probability. And negative probability is definitely unphysical, right? So does this tell me that the Klein-Gordon equation is unphysical? So this was the issue. What are these negative energy solutions or these negative probability solutions that are admitted by the Klein-Gordon equation? So the interpretation or the solution to this problem was given by Feynman and Stuckelberg independently, actually, who said that the negative energy states are actually particles which are moving backwards in time. Uh, in the sense of by particles moving backwards in time, I just mean that they are charge conjugated, as we saw in the previous lectures. Essentially, they said that the negative energy solutions correspond to something like antiparticles. Now, I'm just going through this a little fast now, but soon you'll be looking at something called the Dirac equation, which was written to describe spin half particles. And there, this problem was even more pronounced. Dirac was actually trying to kind of get rid of these negative solutions and realize something very important about what his equation would look like. And that's something that you'll be seeing in probably this week's lectures. Okay. So the point is that when you have a particle moving in this way, right, moving from this way, say the momentum in this way, that's equivalent to an antiparticle moving this way. That's what we mean by backward in time, right? The momentum pointing this way, an incoming positive energy particle is the same as an outgoing positive energy antiparticle. And these are the solutions that we are interpreting to be negative energy simply because we are assigning the wrong kind of nature to them. They are not particles moving backwards in time, they are antiparticles moving forward in time. So this is the kind of insight that Feynman and Stuckelberg had. Again, this, if you don't understand fully, don't worry about it. This is going to come up again in the context of the Dirac equation and the Dirac sea. So we can try to look at this again or revisit this issue again at the meantime. So then, it looks like Klein-Gordon is still fine, and in fact, the Klein-Gordon equation is a perfectly valid equation. It's actually applied to scalar fields, which are spin zero fields. So why Klein-Gordon should correspond to scalar fields? Because again, remember the whole point of field theory is that we write a Lagrangian density that describes the field, and from that Similar to how we do classical mechanics, we just plug it into the Euler-Lagrange equation, and from that we get an equation of motion. It turns out that the Lagrangian that leads to this kind of equation of motion, that is the Klein-Gordon equation, is a scalar field's Lagrangian. So basically, a scalar field is one which has spin zero, and the Klein-Gordon equation ends up being applicable for scalar fields. Okay. So, right. So that's all I wanted to discuss in regards to quantum field theory and some relativistic quantum mechanics. Again, I have not gone into full details. If I this is just like a half an hour, 1 hour discussion of quantum field theory. If you're interested in quantum field theory, it is a course on its own. So I would encourage you guys to look that up on your own time. But for the purposes of the standard model, and to write down the standard model Lagrangian, or to describe the interactions between particles in the standard model, this level of quantum field theory is fine. If you are interested, I would again, a lot of the pedagogy that I've picked up here, actually all of it I would say is from this book, which is Quantum Field Theory for the Gifted Amateur. Again, just to be clear, this is not a QFT textbook. This is a well-written textbook where a lot of QFT ideas are simplified so that you can get a quick idea of them. But if you want to actually learn QFT and all its intricacies, you do have to pick up an actual QFT textbook. I'll give you some resources for QFT also at the end, apart from Peskin Schroeder and the Cedrinki or whatever is recommended in the course. Some like more pedagogical references I'll give you at the end. But for now, let's just go to the question solving part of the session. So as usual, I'll show the question on the screen and you guys can answer in the chat. Let's keep it interactive as usual because it will help you when you are solving your assignment problems as well. Okay, here's the first question. In deuterium, exchanging the neutron and proton induces any answers in the chat? Okay, someone says C. D. Okay, I see one more person say C. Sorry, 1 second. Yeah, sorry. Okay, I can see two people saying C, one person says B, one person says D. Okay, so Uh, okay, I don't have the Hamiltonian right away, but it's made of one proton and one neutron. Basically. And there's an electron as well, but yeah, you have to. Here we are talking about the isospin or the spin. So, okay. Okay, I'm going to go to the answer. So the answer is actually a negative sign in the isospin wave function. Okay. So the way to think about this is that we know that overall we need to have a negative yes, exactly, since both have the same spin. So here basically the thing is that we have to think about it in terms of first of all overall I need a overall negative sign, right? So here now bro, if I consider both the spins to be aligned, proton and neutron, then by exchanging the spins I get, so you already saw in the lectures about how neutron and proton you can, the both the di-neutron and the di-proton cases don't have stable states at normal energies because they require some higher energy states to exist. But the point is that you have one proton and one neutron where both of them have spin half, right? The intrinsic parity of the deuteron is 1 because both of them have plus 1. So altogether we have we have to now combine the spins together, right? So you can either end up with a singlet state or a triplet state because half plus half can give, either 0 or 1 from the angular momentum addition. Okay, so again, the way to find out the parity of a state is to take minus 1 to the power of L. So from that, you can find out that the singlet state is actually antisymmetric, whereas the triplet state is symmetric, right? And we want the overall function to be antisymmetric. So now we have the spin thing, which is giving us whether symmetric or antisymmetric based on the addition of the what is it called? Addition of the angular momenta. Then you have the spatial based thing and you have the isospin. So you have to combine all three of these wave functions together to get an overall negative sign. So you have the space wave function, you have the spin wave function, and you have the isospin wave function. So I already know the spin wave function has to be either, the spin wave function is going to give me a negative sign. The space-based wave function, because it's two fermions, I'm going to be exchanging them, even though they are a proton and a neutron, because they have isospin symmetry. When I exchange them, the Pauli exclusion principle still holds. So the space-based wave function also gives me a negative one. So altogether, I still need a negative one in the isospin as well. Then only I can get a overall negative sign. So this is how you have to think about it. So I already have a negative sign from the fact that the Pauli exclusion principle is there. I have a negative sign from the sort of the aligned spins of the proton and the neutron, which is giving me an overall zero singlet state. And then finally, I have to have a negative sign from the isospin that can only make the overall wave function give me a negative one because minus 1 times minus 1 times minus 1. Okay. The other triplet states are what lead to this neutron, di-neutron, di-proton kind of thing, which is the case. So B is also correct, right? Okay. So, I don't know if exchanging the neutron and proton causes a negative sign in the spin wave function as such. Uh, Let me think about this. Yeah, I'm not sure about this. I don't think that's correct. I think the spin wave function is not sensitive to exchange. It's more about the addition of angular momenta, right? So there, it's not going to go from being antisymmetric to symmetric just because I've exchanged the neutron and the proton. Exchanging the neutron and proton can cause value change in the isospin function. So that's based on the isospin of because the neutron and proton have different isospins, whereas the spin is not going to change on exchange. That's what I mean. So the negative sign in the spin wave function comes from the fact that when I add up the spins, the half plus half is giving me 0, which is minus 1 to the 0 or 1, right? From that fact, I get it. Okay, cool. So yeah, this is to do with the again the angular momenta addition and the overall negative wave function behavior. So you can look at I think it's there in Griffith's chapter 4. There is a discussion on isospin. You can just go and take a look on it. It has this Gelman Nishijama formula and all those other things as well. Okay, no questions. I go to the next question. Okay. There are four species of baryons classified by electric charge. This tells us, okay, sorry. There's a missing thing in the question. This should be delta baryons. Okay. So there are four species of delta baryons classified by electric charge. This tells us that the total isospin of delta is. Okay, someone says C. Okay, someone says 3 by 2. Any others? I don't see any other answers. The answer is actually 3 by 2. So yeah, the types of delta baryons are basically here we are talking about all four species of delta baryon, which is, the delta plus plus, the delta plus, delta zero, and delta minus. So so basically the idea is that the multiplicity of the sort of isospin states is similar to spin states, right? It's 2i plus 1, whereas spin is also 2s plus 1. That's why, for example, here also in the first question, you can think of it also as, so the neutron and proton can combine to give isospin of, let's say, 0 or 1, for example, because you have the up and down quarks, which are there are two isospins which are combining, again, from angular momentum algebra. So if you have something like 2i plus 1, that's going to give you minus 1 to the power of 2i plus 1, that's always going to give you a negative value. So that's why there's a negative sign in the isospin wave function based on the multiplicity. So similarly, if you use the same kind of multiplicity argument, then you know that if I need to get 4 species of delta baryons, then the isospin has to be something like 3 by 2. Then only I will get 2 times 3 by 2 plus 1 is 4. Yeah, there is a negative delta. So there are 4 delta baryons. So there's delta plus plus, delta zero, like the neutral one, and delta minus. Those are the 4 species of delta baryons. So delta baryons also have up and down quarks, but instead of combining to give spin half like in neutron and proton, they combine to give spin 3 half. That's the difference between delta baryons and protons and neutrons. That's why they have isospin also 3 half. So they result in 4 sort of multiplicity states. Okay, is that fine? Okay, I don't see any questions. Next question. Which of the following observations are explained by theories involving fields that are quantum operators? Essentially, quantum field theory. Here, because it's which of the following observations, there could be multiple correct answers, not just one correct answer. So read carefully and answer all the options that are applicable. It's not just one option here, it's a multiple select question. Okay, someone says D and E. Others? Okay, someone says A, D, and E. Okay, someone says all of them. A, C, and E. Any others answers? All of them except D. Okay, I think we can go to the answer. So I think one of you did get it, which is it's all of the above. Okay, so it's a bit of a cheating question, but all of these are actually provable by assuming fields that are quantum operators. So we already saw about antiparticles, how they show up in solutions of relativistic quantum equations. For example, the very first relativistic quantum mechanic theory we wrote down, which is the Klein-Gordon equation, naturally led to negative energy solutions. And that was very important because they had interpretations as antiparticles. As I said, this week you'll be learning about the Dirac equation, and then in the Dirac equation as well, you will find that antiparticle solutions naturally come out in some sense. Variation of coupling strengths and masses with energies is something called renormalization. It's also something that comes in at quantum field theory level. As I said, in quantum mechanics, we deal with Hilbert spaces where we have conserved particle numbers and processes that conserve particle number. When we move to quantum field theory in I keep saying Hawk space, Fock spaces only, we actually find particles numbers changing and other kinds of process happening. Also, complete indistinguishability of particles of the same species, although it's assumed in quantum mechanics, the answer for why that is actually comes from quantum field theory, where we understand that particles are simply excitations of a field. So we can understand why, all electrons are the same, because they are all excitations of the same underlying quantum field, right? Spin statistics theorem we have already explained last week that it comes from quantum field theory only. And the equivalence of forces with exchange of particles, again, because now we can write down interactions in terms of Lagrangians and Lagrangian field theory, quantum field theories and their Lagrangians. We can then quantize those field theories to get the excitations, which are nothing but the particles. So an electromagnetic interaction can be thought of as an exchange of photons, because the excitation of the electromagnetic field is what gives us the photon. So all of them are come up because of quantum field theory and the field interpretation of quantum mechanics. Okay, let's go to the next question. Which of these sets has equal dimensions in natural units? Okay, someone says A. Give me a second. Yeah, which of those? So natural units, as I said, is when H cut and C are 1. Someone says D, D, A. Okay, maybe we can go to the answer. So the answer is actually D. Again, you can try this out and see if this is true or not. I'll leave it to an exercise for these. But basically, you can think of as H cut and C are 1. And so the energy density and pressure have the same units, because you can think of uh, basically pressure is nothing but rho C squared, right? because dp d rho is c squared, right? If you think about like sound speed, for example, dp d rho is cs squared. But if you generalize that to relativistic systems, dp d rho is actually the speed of light squared, and now you have speed of light to be 1. So p is nothing but rho, which is mass density, and because E is equal to mc squared, that is nothing but the energy density. So pressure and energy density have the same units. And similarly, the Lagrangian is nothing but L times d for x. And that is giving us the action. Sorry, L times dx, which gives us the action, right? But here again, you can think of, sorry, L times dt, not dx, dt, which gives us the action. But again, you can think about it in terms of setting the speed of light to 1, and that gives us the same units as well. So you can try it out. It's just a small exercise to see whether they have the same dimensions or not. You can actually just search for natural units, and you will find these tables online where you can convert one quantity to the other and see how it works out. So I'm just explaining just the energy density and pressure simply, but you can try it for the other things as well. Okay. Okay, next question. The Klein-Gordon equation describes which of these states? Okay, someone says C, C, B and C, Higgs, that is spin zero. All. Okay, someone says all of them. Okay, so go to the answer. So the answer is actually only the Higgs boson. Uh, as explained in the slide, the Lagrangian that leads to the Klein-Gordon equation is applicable only for scalar or spin zero fields. Here, of course, we know that the electron and the delta baryon are not it because they are fermions, so they are definitely not spin zero. The Z boson is actually has spin 1, and I think the rho meson also has spin 1, and the Higgs boson is only particle here which has spin 0. So that's why this the Klein-Gordon equation is only really applicable for the Higgs boson in the standard model, because all the elementary particles have spins other than 0. But yeah, I think the rho meson also has spin 1, so it's not applicable for that as well. I'll just check that very quickly. Spin of the rho meson. Yes, the rho meson has spin 1. So it's only applicable not for all bosons, only for spin 0 bosons. And that's why it's only applicable for the Higgs boson. Okay, fine. Next question. Which of these terms cannot be part of a Lorentz invariant Lagrangian of spin 0 field phi? Any answers? C, as it's not contracted. Okay. Any other answers? C. Okay. Someone else says C. Okay, guys. I think you all got it. The answer is C. You're right. This is not contracted, so this is actually a vector term, right? So we know that spin zero terms behave as scalars. So remember, if it's Lorentz invariant, scalars have to keep their behavior under parity transformation. This is a vector term, and it's not contracted, so it's not consistent with the Lorentz invariant Lagrangian of a scalar field phi. So spin zero means automatically you have to think of scalars. Spin 1 is a vector field. Okay, so that's how you think about it. Again, just think of sort of relating spin with the sort of scalar, pseudo-scalar, vector, pseudo-vector behavior we spoke about before. Also, I just checked because I felt like I got it wrong and it is actually wrong. So in this question, the answer is actually A. I'm sorry, I saw energy density and pressure and I put them together. But while looking at it, I was confused because the action is supposed to be dimensionless, whereas Lagrangian has some quantity of energy, some dimension of energy depending on what the system is. So I'm sorry, I made a mistake, I think, while marking the answers or solving. I saw energy density and pressure. So energy density and pressure actually do have equal dimensions in natural units. It's just that the Lagrangian and action do not. So I missed that. I think while making the slides, I missed that. But it's actually this. And this you can understand because E is equal to PC plus mc squared. So energy, momentum, mass all have the same. Temperature is related to the kT kind of value, and K is also set to 1. And inverse time is also the same because of, you can think of it in terms of the action, right? So that's why all of them have the same unit. So sorry, I made a mistake before. I just looked at these two terms and kind of marked it automatically, but it's not, it's actually E. Okay, sorry about that. Okay, yeah, so good exercise to check if I made another mistake, but please call me out if you find me a few mistakes. So I make these slides and sometimes I, miss something or the other. So yeah. Okay, so this question, as I think everyone answered correctly, is that it is actually C because it's not contracted. This is a vector term. A vector term cannot be in a scalar theory because they have two different behaviors, right? Okay. Next question, a scalar field has a mass dimension of what? Okay, someone says B. B. Okay, another person says B. Okay, we can go to the answer. So the answer is actually B. So again, you can see that the action is something like d power 4 Lagrangian, and the Lagrangian has to have e power 4 kind of energy. Then only because again, if you use natural units, energy has the same units as inverse time or inverse length. So that, and you know that a scalar field is described by the Klein-Gordon equation. This is nothing but the Klein-Gordon equation, right? With some half fact. So this is Klein-Gordon equation. So if you want a Klein-Gordon like term, then that means that this whole term has to have e power 4. We already know m squared has e squared because e is equal to mc squared, c is 1. So it has a dimension of energy squared. Du also has energy because it's inverse of length, which has the same dimension as energy. That implies that phi should have energy to the power plus 1. So this is how you calculate the mass dimension of a scalar field. Okay. So again, this is easier to do if you just assume natural units, and it's done. Actually, it's done using natural units. So you can try this out. Okay. And again, this is particularly in 4D, right? If you change the dimension, then this D4X is going to change. So that means that the value is also going to change. And actually, you can generalize this to n-dimensional theory. Of course, don't worry. We live in a 4-dimensional world, 3 space dimensions and 1 time dimension. So in this course, you're only going to be seeing 4D, but you can still, for mathematical interest, you can try to generalize this result to D dimensions as well. Okay. Okay, fine. Next question: why is it bad to have a Hamiltonian with a square root of terms that contain space-time derivatives? Okay. Okay, A and C, A and C. Okay, so there's only one answer in this, I think. So I don't think you have to put two answers. Okay, we can go to the answer. So the answer is non-locality, right? So, right. So here you can see that again, even though we have, okay, not here, here. Even though we do have, it looks like we have space and time look different, but overall they do still have the same footing in the sense that this is del by del t and this is overall del by del x because it's like del squared root, right? The problem is that as we pointed out during the lecture, if you expand this you get higher and higher derivatives of x, which again definitely puts it on a different footing. But more importantly, what that now means is that a particle at a particular point, its behavior depends on higher order derivatives, which means that we have to now take into account all over the field, right? All over space and time, which is non-local. Which non-locality basically means that nothing can affect things beyond the speed of light, which is kind of what this sort of infinite derivatives is implying. It's implying that I now am depending on infinite number of derivatives, which means I'm depending on all over the space around me, which is not consistent with locality. So even though this equation on paper looks like space and time are on equal footing, of course, I have to then think about the expansion and the infinite series and what it implies. So the answer is actually the first option A. Okay, is that fine? Okay. Yeah, I mean, C kind of gives A, but even if C was perfectly okay, if you still have like, if you have infinite amount of coordinates on both sides, then also it's not going to help, right? Suppose I have square root of time and square root of x, then I'm still going to have this issue. Even though position and time are on the same footing, I still have this issue because I still have this infinite kind of derivative issue. Suppose a whole thing is under the square root. In the Klein-Gordon equation, we had only the spatial part under the square root, but not the time part. But even if the whole space-time derivative was under the square root, we would still have this issue because this non-locality would show up because the derivatives, infinite derivatives implies that the process that's happening at x actually requires inputs from all over the field, which is non-local. Okay, I hope that clarifies it. Okay, awesome. So next question. Oh, sorry. Yeah, next question. A 0 point energy that contributes to dark energy density exists for what kind of quantum fields? Okay, someone says all bosonic fields. Okay, someone says D. Others don't seem to have answered yet. Maybe we can go to the solution. The answer is fields of any spin. So the 0 point energy or the vacuum energy kind of thing comes from basically the lowest energy level, which is not always zero because you have this sort of basically because you have a discretization of energy levels, right? For example, in harmonic oscillator, the reason why the 0 point energy is half h cut omega is because we actually have a discrete set of energy levels. So the energy levels don't just go to zero. Similarly, in the hydrogen atom, ionized hydrogen atom, for example, you don't go to zero, you have these ladder of energy levels, right? So as we saw in, the beginning when I was trying to motivate quantum field theory and second quantization or canonical quantization to you, we can always write a field theory in terms of eigenmodes, and then we can quantize those eigenmodes to obtain the sort of energy solutions in terms of, sort of quantizing the field to give particle solutions. So that's true for any spin, right? The only thing is when you combine the harmonic oscillator eigenmodes, so to speak, for fermionic and bosonic spins, you have to take in mind that, you have to keep in mind that the overall behavior should give this anti-symmetry in fermionic systems and symmetry in bosonic systems. So the way you arrange your harmonic oscillator eigenmodes may be a little different in both of them, leading to what is the spin statistics theorem. But the 0 point energy concept is applicable for both of them because both of them ultimately can be discretized or can be quantized into this ladder of energy states. I hope that's clear. So this exists for all quantum fields. Okay. I hope there are no questions. I'm going to the last question now. Okay. Someone says B. Any other answers? A. A. Someone else says B. Okay, maybe I can go to the answer. So the answer is actually B. So again, this is again when we are constructing our eigenmodes of our system, we are essentially building up a system of many harmonic oscillators. Remember, so the different harmonic oscillators are each independent of each other. So the dagger of so the this is always forget this is a creation operator of two of the eigenmodes are independent of each other, right? So that's what this represents. Okay, I hope that's fine. Okay, great. So I'm done with what I wanted to discuss. I had a few slides on group theory, but I think it's already like quite late. I'll quickly go through this. So as I said again and again, the group theory is what leads us to, describing the standard model in general. It's a mathematical language we use to describe the standard model. You've already got some introduction to groups. Particularly now we are moving on to Lie groups. Lie groups are basically continuous groups. The mathematical definition for them, as with all things in mathematics is more complicated. But for your purposes, we are moving from discrete symmetries like charge conjugation or parity. We are now moving to continuous symmetries. And that's why Lie groups are useful, because they are continuous groups where they depend on continuous parameters. And every Lie group has an underlying Lie algebra. And we are going to be using that kind of concept to write down the different interactions in the standard model. Because, as I said, different interactions belong to obey different symmetries or belong to different groups as such. One important concept when it comes to Lie groups, which we can discuss maybe next week because today we are out of time, is the concept of generators, and also the concept of representations, which is that, a group is an abstract concept, and then you can represent a group in different ways, right? Like SU2 is an abstract concept, and then you can represent SU2 by some matrices, or you can even represent it by some other mathematical object. But that is the idea. So you can always change from one representation to another. So for example, you can see that this is a particular set which forms some particular group, but then you can also represent the same group by some different set. You can represent it even by R cube. So in different vector spaces, the group can take different forms, is the idea. So this is all some mathematics. I thought we'll have more time today. So I'm not going to go into this, but yeah, you can go through some things. So maybe we can pick up again next week about Lie groups and group, little bit of group theory, like how today I gave you a little bit of QFT. Again, if you're interested in QFT, pick up a QFT textbook. But if you want to get a flavor of what QFT is like, I would really recommend QFT for the gifted amateur. As I said, it's a very shallow book in that it covers a lot of things but not in much detail. So if you want to go deep into something, of course, you have to take a QFT class or, course, or take a QFT textbook, but this is a very good book for what it is. There is a YouTube channel by this name of this professor in the US, Alex Flournoy. Um, Particularly for group theory, I found his lectures very useful and interesting. But he also has a whole class playlist on particle physics. I watched a few of his lectures when I was taking my particle physics course as part of my PhD coursework, and I found them interesting, but I don't really remember that well now which videos were which. But I remember the group theory videos. I've linked them here to you. David Tong, who I'm sure all of you know, has some nice QFT notes which go into a little more detail. There's this book called Symmetry and the Standard Model by Matthew Robinson. Particularly, chapter 3 of this book has a lot of group theory, which I really appreciated. And this book called Lie Algebras in Particle Physics by this person has a lot of mathematics, but from the perspective of the standard model. So you can try to look at these resources. These are on top of the normal resources that you have. So obviously you can continue using your, Griffiths and Cedrinki and other things, but this is like some additional things, and particularly some more pedagogical kind of things, so that if you find yourself stuck, you can go to these resources if you want. Okay. So that brings me to the end of today's lecture. So thank you all for joining. So if there are any questions, please let me know. Otherwise, I'll just share again the links in the chat. So this is my mail ID. Please mail me if you want me to discuss anything in more detail, or if you find any flaws in what I said. I'm not a particle physicist, so I may make mistakes in my slides or in my, today I found a mistake while I was discussing. So, I make these slides in between my work week, and then sometimes I may make mistakes, so please call me out if you find any. But in general, yeah, if you want me to discuss something, I'll make the best of my ability to make some slides and discuss it. We can have an interactive session. Apart from that, this is my website. As I showed you in the beginning, if you go to my website, there are the links to the recorded videos and the slides of all the sessions so far. I'll be uploading today's video as well by today, by probably by tomorrow it will be up, and I'll put the slides as well as that point, so you can see here that, particle physics and the standard model, the YouTube playlist is here, and also the slides of the sessions are here. Okay. So yeah, that's it from my side. Any other agenda for anyone? Okay, fine. If not, have a nice rest of your week. Thank you everyone for joining, and I'll see you again same time next week. Okay? Thanks everyone.
Thank
Bye.
you. Bye.